Good afternoon, students. This is EE 330, Chapter 1. And we're going to start with ideal diode. What is a diode? Diode is a two-terminal device designed to conduct current in one direction only. So usually if we have this diode here, so if we introduce the positive in this direction, it will go through, and this is the anode terminal, and this is the cathode terminal. So unlike the resistor, so resistor is just like it reduces the current intensity, and diode which conducts in either direction. So if we introduce the negative here, it will go through. So if I put on the current and voltage, this is voltage. So usually this is the all region for the anode. So usually that's from A to C. So let's say from terminal A to terminal, let's say B. So usually in this region, the diode acts as a short circuit, A to B. So we have a positive, negative, works as a buffer. This is the on region. This is the on region. And here, this region is the off region. They call it cutoff, which is CO. So in this, if we introduce the positive from this side, let's say B, the diode will work as an open circuit. So there is no current flowing in this direction. So the current will flow from this direction if the voltage is introduced from anode to cathode. And there's many applications that we can use. We can use the diode to achieve certain components in the circuit. Let's say an example of a diode application. So if I have a circuit that I need the positive here and the negative here all the time, and I don't know if the user is going to put positive or negative on this terminal, and positive and negative here, so this is negative and positive on this terminal. So no matter what, I want the positive to be here and negative to be here. So to accomplish this, all I need to do is put diodes in this format. So what happened if I introduce the positive or negative? Anyway, the positive will go this way, no matter what, and the negative will go this way. Same thing here. The positive will always go in this direction and negative will go in this direction. So usually I will always have a negative here and positive, and this is a good application for DC. So talking more about the voltage across the diode is defined as positive here on the anode and negative at the cathode. Conforming to the positive sign convection of other popular devices, like we can say the transistors in other buffer-like devices. Okay, so most likely, if we need to talk more about the diode, we can introduce the diode as a circuit. Let's say this is a source, voltage source, a diode, and a load. What happened here? The current will flow always in this direction. So what happened if I flip this diode? So there is no current will be flowing in this direction. So if I put this is our load, so there is no current is equal to 0 that will be flowing in this direction. So the idea of the diode positive, negative, let's say we're going to call this one as an open circuit voltage. And we're going to introduce the circuit with whatever resistor in the circuit, and we have a diode. Any components in electrical engineering that current run through it, it have to be consuming voltage. So the current will run through this because the positive will go through. This is what we call linear circuit. If you took 211, you should remember Thevenin circuit. Let's introduce this into an operating point. Let's say this is page 1. We still continue on ideal diode. Continued. This is in chapter 1. So let's say we have, this is the current and this is the voltage. So when the open circuit voltage is greater than 0, we're talking about this. This is the load. And let's say we introduce the diode here, R equivalent. This is a linear convention circuit or Thevenin circuit, where we have, this is positive, negative voltage, and the current going through this side. So when the operating, this is the VOC, when the VOC is greater than 0, that means the voltage V is equal matching the VC. So let's say at this point, this is operating voltage for the diode. And in terms of the load, there's an operating point. If it's not on the positive side, it should be on the cutoff side. So usually, let's say if we are talking about, let's go back here. I think I forget to mention that when the current or the voltage is introduced in the positive direction here, we call this one forward bias. Forward biased. If we introduce the negative on this side from the diode, we call it reverse bias. So at this point, we have the current is equal to 0, and the voltage is less than 0, which is negative side. On the forward bias, we have the current is greater than 0, and the voltage is greater than 0. So at this point, this is forward bias, and this is reverse bias. So going back to the operating point in the forward bias, so let's say we have the operating point, I'm just going to name it as a QF. So between this voltage, this is the load line. This is a load line for the diode, and this is the operating point. So if I reverse this, my scenario will be a little bit different. So my voltage, sorry, this is a voltage. So my voltage will be in the operate, let's say VC is negative, is less than 0. So VOC is less than 0, which is, let's put it here. And let's say my operating point in this range. So let's say this will be my load line. So this is my VOC. Also, this is the reverse biased operating point. This is the forward biased operating point. So most likely we have the operating, the voltage source and the operating circuit will be less than 0. That means V is equal to VOC. So let's see, this is OC for open voltage, open circuit voltage. So in this term, we take, when we have this mean a short circuit, and this will mean an open circuit. This is for the forward bias. On the diode, and this is the reverse bias on the diode. So I'm going to take first for V, the open circuit voltage is greater than 0. This is my first case, and I'm talking about when VOC is greater than 0. What happened at this point? So at this point, the voltage is equal to 0. We have a current running through. So that means we can solve for the current from the linear circuit, which is VOC, just using Ohm's law. divided by R equivalent, and this should be greater than 0. For V operating or open circuit, sorry, voltage less than 0, we have an open circuit. And here I wrote it again, it should be short circuit. And here should be open circuit. This is my second case. So what happened here, there is no current running through the diode. And in this case, the voltage will match and they will be less than 0. So most likely this is for the ideal diode. This is what you need to know about the diode. Let's recap. Ideal diode is a diode with two terminal devices designed to conduct current in one direction only. When it's conducting from this direction, that's a forward bias. That means the current is greater than 0 and the voltage is positive side, on the positive side. So most likely this side here is the short circuit side. And let's say this side here is the cutoff, which is the diode is off, which is open circuit. A very, very famous circuit for the diode is the bridge diode circuit with 4 diodes, and you can accomplish any terminal to be on any positive or negative on any one, will always give you a fixed positive here and a fixed negative here. If we put it in a linear circuit, if the source is feeding the load through the diode, if the diode is aligned with the forward bias of the current will pass through and we have a short circuit and the load will work. If we reverse the direction of the diode, nothing will be happening. Everything stops here. The diode will work as an open circuit. The diode here works as a short circuit. And to continue more, this is the load line for the linear circuits. As we said, this side here is the short circuit side, and we have this side is for the cutoff, which is open circuit on a load line for the operating point. We have two cases. When the open circuit voltage is greater than 0, everything runs normal. So we can calculate the current when it hits the load through Ohm's law. When we have the open circuit voltage less than 0, nothing will happen. So the current is 0. So this is page 2. Let me change the page. Page 1 and 2. Page 3. Ideal diode. We continue on this. Okay. Let's say we have a signal on the input side that will be sine wave. Okay, so it's going to be just to show you the functionality of the diode. This is then the input side. Let me put a cross in the bottom here. This is for sure due to time because It varies with time. So this is our output voltage. And this is for the ideal diode. So I'm just gonna digitize this to show you what happened. Let me try to bring okay. So this is for, let's say, voltage source here. I'm gonna call it V1. And I have a diode here and a load here. So most likely the current running through here. If I have my diode in this position, the output voltage will be introduced because this is in a forward bias direction. It will only take the positive, because if you look at this, we have positive, 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 and we have negative, negative, and also we have here negative. So what happened is for ideal voltage, remember guys, for ideal voltage, we are considering VB is equal to 0. So there is no delay when it comes to rectifying the output. So most likely, I'm going to put it in this color. I want to introduce usually 0.7 voltage for the when it's VB is not 0. So usually the output signal will be rectified as a positive clipper. So it's going to be like this. Nothing here because it won't pass because of the forward bias. Doesn't pass it. And my output signal will be in this form. So what happened, this is for ideal, when we have VB is equal to 0. What happened when this is V output? What happened when we have VB is equal to 0.7? So you hear this a lot. The base voltage, the bias voltage will be 0.7. That means there's a delay here before it responds to the positive signal, and there's a delay here. So nothing passed here, and there's a delay. Oh, sorry, this is nothing passes here, and there's a delay on this signal, and so forth. So this is what we call the positive rectifier due to the diode. Let's say I reverse this diode. Let's say I took it off and I reversed this in this term. So what happened? This signal, the output for this signal, I'm going to put it in green. It will be in this form. Nothing will happen in the forward bias, and it's all reverse biased. So this is my signal in green for this direction. I hope you have a better understanding of how the diode work in rectifying the input signal to the output signal. When it's in forward bias, it's only identifying the positive signals. When it's a reverse bias, this is the reverse bias, the one in green. And remember 0.7 usually when it's used with silicon. Every time you see a silicon, it's going to be 0.7 delay. If you're using germanium, it's 0.3 volts VB. So don't worry about it unless it's mentioned in the problem. Okay, so let me give you a circuit and try to analyze it through a different format, and I put the wave signal. So that will be, you will understand it a little bit better more. Let me put a new page here, page 3. This is page 4. We're still working on ideal diode. It's very important, guys, to understand the diode completely. If you don't understand or you have anything to clarify, please, during the office hours, or maybe request, we can go on Zoom during the class hours, and I can explain further more if you don't understand. Let's say we have this circuit. I have a diode in this direction, a node. I have another diode here in this direction. And I have another diode in this direction. Let's say I put a resistor, another diode here. I'm gonna flip it. So the voltage across is usually always positive, negative here. Positive on this side, negative, positive, negative, positive, and negative. So let's say this is our equivalence, and there's an output voltage on this side. So I'm gonna name my diodes. I'm gonna name that this is my D1, D2, D3, and D4. This is input voltage, output voltage. So in this manner, I have two cases. One, V1 is forward biased and V1 is reverse biased, right? So we're gonna take the first one. For V1 is greater than 0, how my circuit will work, pay attention please. This is my voltage. I'm gonna put it here. This is fixed. I'm just gonna put these, and then I connect the dots later on. Okay, I will let you know. This is D1, D2, D3, and D4. Okay, don't look at this one, so we will go on here. So for V1 is greater than 0, that means it's forward biased. Forward biased, that means when the diode is introduced, the positive in this direction, the diode will work as a short circuit. Remember? Okay, so the current is running through here. So when it hits D1, D1 will be on or off? D1 will be on or off. For sure will be, this is forward biased. It will be on. It will be short circuited. So the current will continue, and it hits D2. D2, for sure the current will be splitting, but still some current goes through here, it won't do anything because this is reverse bias, so this is on open. Okay, and then the current passes through here, and this is reversed, so it will be open. So the current will pass through here. D4 will be short-circuited. So my current will start here, continue here, here, and then here. So this is the path. I'm gonna put it into in this color. It's gonna be like this is for the forward bias. So my output signal, and ideal, I'm not gonna worry about, so I'm gonna put the input signal here and the output signal here due to time. V1, here's V output. So my input signal is this, V1. So I made it a little bit bigger. So let me try to make the signal okay. Try to do my best. 1, 2, 3, 4, 5. Okay, this is better. So I'm gonna digitize it into my output signal. So when this one hitting the first diode, it will be forward biased, right? That's D1. On the first run, D2 is off, right? D4. D4. And then off, and then D1, and then off, and so forth. So this signal, I'm gonna put it in black. This is for V1 is greater than 0. I'm gonna put the second case here for V1 is less than 0. That means reversed biased. Okay, so I'm gonna make the circuit a little bit shorter. Positive, negative, V1. Okay, this is R, positive, negative, VO. That's the current. Okay, so when this is reversed biased, we're looking at this circuit here. So the circuit going through here, reverse bias, that means D2 will be short circuited, right? D1 will be open, continue here. D4 will be open, D3 will be short. So this is forward bias direction. This is reverse bias direction. So what happened here is when V1 is less than 0, you can start from this direction, but you have to reverse the polarity of V1. If you want to keep it, you have to go the other way. So most likely the direction of it's going to be like, so I'm going to put this one into, so usually D1 will be off. This is D2. D4 will be off, and D3. and then D1 kicks on because it's going to be off on the reverse bias. So most likely this is reverse bias, forward, forward, forward. So this is my output signal will be clipped into a rectifier. So most likely the output will be the absolute value for the V1. So all of the signal in the negative will be implemented in the positive. So that means V0 is equal to V1. Okay. So now we're going to go into this is page 5. We're going to go to the diode logic gate. We're going to implement OR gate into diodes. Hope you guys still remember EE201. For, let's say we have a gate of 2 inputs. This is an OR gate. So A or B, if we are talking about 2 input system, here, this is the input side, and this is the output side. So 0, 0, 0, 1, 1, 0, 1, 1. So usually all of these are the different combination on the input that if we turn off this, meaning we put 0 here or 1 here, 0 means off, 1 means on. So what's the output here? So we know that the OR gate, any input with 1, either or will give you 1. So to implement OR gate into diodes, so we have A, B, diode here, and both will be, and for sure we have a resistor between the output and earth or ground. This is the output signal. So whatever input here, after the diode, we're gonna call it diode A output, diode B output. So I'm gonna put this one into A, B. This is in terms of the gate. Remember guys, 0 is low, 1 is high. High, it doesn't matter, it could be 5 volts, 9 volts, 12 volts, any volts. Low is 0. And we're gonna take a look after the diode. So DA, DB, and the output. Okay, so this is how it's gonna work. Pay attention. I'm just gonna implement this into AB because this is fixed. This is most likely the logical combination that on the input side will be possible. We only, if we're talking about 2 input, so we only have 4 possibilities. So this is going to be low on 0, low on 0, low and high, high and low, high and high. Okay, so if we introduce low and low on the first case here, 0 and 0, for sure both of the diodes will be off in the cutoff region. So the output will have low. If we have A on the low, that means it's off, and high on B, the diode, if we introduce high on B, the diode for B, the output on the B terminal will be on. The diode is short-circuited here. So most likely, we have a high on the output. So for the one who did not understand these two, I'm going to concentrate and elaborate a little bit more about how we're going to get this here. So I'm introducing high to A, high, which is mean 1. And I'm going to introduce low, which is 0. So most likely this is forward bias, so most likely this will be acting like a short circuit. So DA will be 1, which is on. And for B being low, 0, this is going to be acting as an open circuit, so this is off, which is CO, cutoff region. So most likely this is going to be high or on, and this is going to be cutoff, which is off, and the output will high because remember guys, for OR gate. So the other one, high will be on, and high. So this is most likely to introduce the diode logic gates as an OR gate. Now we're gonna talk about the diode as a diode logic as an AND gate. Remember, in digital design, we have two inputs, AND gate, A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. So most likely A and B to have Y on. So it have to be, if you have a 0 in one of them, 0 multiplied 0 is 0. 0 multiplied 1, 0. 1 multiplied 0, 0. 1, 1 is 1. So most likely this is the logic truth table for the AND gate as a digital design. So we're going to implement this one into diodes. So in this term, we're putting the diode into reverse bias direction. And we have the resistor here. This is A, B. Same thing we're gonna do like we did to the truth table, elaborated truth table. So this is gonna be DA, DB. So we have A, B, DA, DB, and we have the output. So most likely 0, 0, 0, 1, 1, 0, 1, 1. So what happened on the output? So if we introduce 0 and 0, so both will work as here. What happened if we introduce 0 and 0 on the first? Because this is a reversed bias and the voltage here is less than 0, that means this is a short circuit, most likely on. Because we're talking about reverse bias, if both are on, it will pass the low to the output. I know some of you will be confused. It should, because this on, this should be passed high. We're already introducing low on the input, and the diodes are reverse bias position. So usually it will pass the low to the output. Let me go to the next one. 0, you should know in reverse bias, it's gonna turning the diode on, and 1 will be turning the diode off. So still we're getting low. Same thing, this is cut off and this is on, we have low. Now we have 1 and 1. Let's see what's going on in 1 and 1. So we have voltage greater than 0. That means we're introducing 1 here and 1 here. So voltage greater than 0. So usually, because we're talking about reverse bias and the voltage here is not passed, so DA is off and DB is off. Because both are off, we're talking, I made a mistake by putting the resistor into the ground, because we're introducing the reverse bias. This is going to be VS. That's why the diodes are, when they're reverse biased, this will pass through. So most likely both diodes are off, so this voltage will pass through the output, so this is going to be high. I hope everybody understood. In OR gate, we short the output through a resistor to the ground. In the AND gate, reverse bias diodes, we short the circuit, the output through the resistor by the voltage source. This could be 5 volts. Any volts is associated with the circuit. Okay, now we're going to talk about, this is page 6. The voltage clamps. Voltage clamps is the unidirectional switch. It behaves, or behavior of the diode can be exploited to establish prescribed limit for certain voltages in a circuit. Let me give you an example. Let's say we have V1 here, and we are introducing a diode here and a diode in this format. And we have an IC here. The IC will have a limit voltage between Vs. This is a voltage range. And the other range will be grounded. That means from 0 to Vs. This IC will perform through a certain voltage limit. So usually, so let's say call this is CMOS, and this is V0. Or we can call it single supply operational amplifier, op-amp. So we're gonna name this one D1 and this one D2. This is a resistor, and most likely this is an input. voltage, and this is most likely external. So in certain situation, for instance, in connection with the input to the integrated circuit, which is IC, which must be within limit as recommended in the data sheet. Let's say this IC or op amp is recommended that stays in between 0 and 10 volts, or between 1 volt and 5 volts, or any range that will keep this component safe. So what happened? This will protect it. And I'm going to explain to you how this works. So most likely, I'm going to put the input voltage. So this is the input voltage. And so there's like a line for the, due to time, because this is alternating signal. Most likely, this is V1. This is the V1 signal. So we have Vs is the limit. For sure, it's going to be less than the maximum voltage. So most likely this is Vs. Okay. So what happened is, if V1 is between 0 and Vs, that means D1 and D2 are off. How is that? If V1 is greater than 0, that means it's forward biased. If V1 is less than Vs, it's reverse biased in case Vs is greater than V1. So most likely, both diodes will act as a clamp. So in this case, we're gonna elaborate that V1 is equal to V for the IC. So most likely, the input voltage have to match the range on the IC voltage, so the output voltage will be safe within the range of the specific whatever data sheet specify that this IC will be operating. So if V1 is greater than Vs, what happened? If V1 is greater than Vs, what happened? So remember, guys, more voltage, less voltage, the current will flow from more to less, right? So in this case, D1 will be forward biased, right? D1 is on, right? D1 will clamp the voltage between VIC and VS. This is VS, and this is VIC, which is V1. Remember, VIC and V1 is the same, so most likely this side here will be clamped. So D1 will be, in another word, working as a limiter. Limiter of what? Voltage to not exceed Vs. So all of these will be clipped off. So the signal will be going through here. I'm going to put it here. So Vs, V1, this is the time. So most likely my signal will be like this. And the mission for D2 will be limiting from reaching below 0. So let's say all of these signals here will be clamped also. It doesn't matter the ratio if this is big or small, but all of these will be clamped as well. So my signal, let me see, I just put more here. So my signal will be into like this. So my output signal will be only the one in red. This is the VIC, which is the output voltage, because the VIC is clamped. This is the mission of the diodes if we put them in this format. So we are building here on the idea of the diodes. We started with a diode as an individual component, and we built on it. We went to diodes as a gate, and then voltage clipper. Okay, let's put, this is page 7. Let's put this into a test by running an example. And we're going to talk about piecewise linear function generator. Okay, so we have this circuit. V1 is the input. So we have V output here, could be going through a different partial of the circuit. We have a diode here. We can put it same as the other one, but just like for the space here, I don't want to go up, so I bend it. Okay, let's put this one into. And I have a resistor here, 10K. And we bump into the problem where so we have a 12 volts here. I hope you can see it. Another resistor, 10K. And a 10K going through the ground. So input output voltage signal. So we have, this is the V input and output voltage. And we have this starting at, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So let's see. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are the input output voltage. So most likely we're going to check. We have the signal, let's say 1, 3, starting on 3, going to 4, and 4. 1, 2, 3, 4. With the signal going like this, and then 8 to 8, 4, 5, 6, 7, 8, 5, 6, 7, 8, and then 9 to 12. This is 12, and this is 9. 12, 8, 8 to 9. 3, 4, 4. Okay, so with both diodes off, okay, we have 20K here. And we're going to name this one as D1 and this one as D2. So D1 and D2 are off, cutoff region. If where these are off, D1 and D2, when V1 is in between 4 and 8. This is V1. D1 and D2 off. That means there's no current for 20 kilo ohm. This will pertain that V0 and V1 are equal for V1 is in between 4 and 8. So let's take the cases one at a time to explain to you what happened when between 4 and 8, when V1 is greater than 4, when V1 is greater than 8, and what happens. So we have 3 cases. Case number 1, when V1 is between 8 and 4. Case number 2, when V1 is less than 4, because this is one case, this is one case, and this is another case. This is V1 less than 4, V1 greater than 8. 3, V1 less or greater than 8. So let's explain these 3 items. So for V1 is between 4 and 8. So what happened here? I'm going to put the circuit plus negative. This is V1, 20K. We have D1, we have D2. This is V0. So you know the values. What happened on D1 and D2? D1 and D2, when V1, what happened when V1 is greater than 4? V1 is greater than 4. That means D1 is off. What happened when V1 is less than 8? That means D2 is off. How is that? Think about it for a little bit. So we're considering that V1 is greater than 4. That means it could be 10, 12, anything. So most likely forward bias on there is no forward bias here because we have 12 here. In order to forward bias on 12, V1 have to be greater than 12. So this is going to be off. And also V1 is less than 8. So it have to be less equal to 0. So it can be short circuit here. So most likely it's open circuit. Let's go to the case number 2. When V1, maybe you understand this is a little bit better when I explain what happened when it's V1 is less than 4. I'm going to keep this one open and keep this one open. We're putting the values right now. So this is, you know, the values. I'm not going to write them. Okay, we have D1 here and we have D2. Okay, this is 20 kilo ohm, 10, 10, 10, and we have 12 volts here. Okay, so V1 is less than 4. If V1 is less than 4, this diode here will be reverse biased or will be off. So this one will be open circuit. If V1 is less than 4, so because this is 12 and this is reverse biased and less than 12, V1 is less than the maximum voltage. So this one will be short circuit. Let me put this third case. For V1 greater than 8. I'm going to leave it open. This is the output. The output. I'm going to leave it open for the moment. 12 volts, 10K, 10K, another 10K. Okay. In this case, what happened to if you do not understand what's going on here, if you don't understand it, maybe you can try to solve it through KVL or KCL, sorry, KCL, which is sum of the input current on the input side is equal to the sum of the current on the output side. So most likely the current on the input side is most likely 12 minus V0 divided by 10 plus 10 plus 10K is equal to, on the input side, or on between V0 and V1, so we have 20 in between. So V0 minus V1 divided by 20 plus V0 divided by 10. So solving for V1, it will be less than 4. Going to this example, okay, I'm going to apply KCL, which is sum of the current that on the input side is equal to the sum of the current on the output side. So V1 minus V0 divided by 20. V1 minus V0 divided by 20. So if this is forward bias is greater than 8, so most likely the current will running through here, V1 will be on, will be off. So, and we have V0 divided by 10. It's going to be equal, sorry. This is on the, yeah, equal. And now we're going to go to 12 minus V0 divided by 10 plus 10. No, not 10 plus 10. It's going to be, I'm confusing you. V1 minus V0 divided by 20. Okay, that's accomplished. And V0 minus 0 divided by 20 here. So this is going to be equal 10 plus 10. And here we need to add another term, that 12 minus V0 divided by 10. 12 minus V0 divided by 10. So we solve for V0 is equal to 0.25 V1 plus 6. With this equation, we know that the diode one will be short-circuited. This is check and true. So most likely, this is the ideal diode into details. Okay, let's solve an example from the problems. Page 6, page 8. We're going to solve 1.2 on page 93 from the textbook. Let me share with you on the textbook the circuit. Okay, it says in the circuit of figure P 1.1, the circuit, let's VS, or let VS equal to 24 volts. I'm gonna go ahead and put the circuit while you guys read through it. VS is 24 volts. And R1 is equal to 300 ohms. R2 is equal to 200 ohms. And we have D1. And we have R3, no values. And 20 milliamp IS. IS equal 20 milliamp. So, no, so we need to find IS for the current on the diode, sorry. So let me erase this one. current here is 20 milliamp ID, current on the diode. So let me put back. So most likely we have 24 volts here, 300 ohm, 200. We have 20 milliamp on the diode going in this direction. And we have R3 here, no values, and we need to solve for IS. Okay, to do this, all we need to do is we have to assign that there's a voltage here. Let me take this D out. So can assign, and let me take, so this is D1. I'm gonna assign my VD, or should I put it VX? That's the voltage across Y, because the current is going that way in a 20 milliamp. So the voltage will be forward biased on this direction. Okay, so if this is forward bias on this direction, so that means this is on. That means this is acting as a short circuit. So we have Vx voltage here. All we need to do is KCL, apply KCL, which is the sum of the currents on the input side is equal to the sum of the current on the output side. So most likely 24 minus V, I'm going to call this one Vx. 24 minus Vx divided by 300. So 24 minus Vx divided by 300 is equal to, we have 20 ohm and Vx, so Vx divided by 200 plus we have, if the current is going away is plus, if it's going in it's negative, so plus 20 milliamp. It's easy, we can solve for V of x. Let me get a calculator. Okay, 7.2 volts. Now, so we need to find I of S. So we have, we can apply the, we have 20 milliamp, we have IS here, and we can, since we already have the voltage here, we can I3, let me show you what we missed. We missed that R3 is 400 ohm. Else we could not find I of S. Okay, so most likely we apply another KCL on this node. Let's call it node Y. On Y, so we have sum of all the input, current input is equal to sum of all the current output. So most likely we have 20 plus I of S is equal to, we have the voltage 7.2 divided by 7, this is 20 milliamp. So if we take the milli here and we'll take, so it's going to be 7.2 divided by 0.4, solving for IS is equal to, so this one minus 20, let me see, it's going to be negative for sure. So 7.2, 0.4, minus 20, oh, 2. It's going to be 2 milliamp. So this is part A. Let's go to part B. Let me share the screen with you. Okay, part B, if I of S is equal to 15 milliamp, find V of S for 4 voltage drop across the diode. This is going to be, I'm going to solve this. And part D is going to be the same as both of these. So I'm going to do, C and D is going to be the same thing. So I'm going to solve this, and I want to put you into the test to continue for solving for part C. So let me do part B. Let me do part B for you. Let me stop sharing this screen. Okay. So on circuit B, we have a voltage drop across the diode. What does that mean? We have -4 or 4 volts reverse bias. So I'm going to put the circuit, the new circuit for VS, R1, R2. This is going to be an open circuit now. And there's like a positive -4 here. 0.4, let's put these 0.2, 0.3. We're going to call this one as VA. And we have 15 milliamp because we're doing all the milli, so it's going to be 15 amp here. So most likely, if I'm looking for VFS, so we're going to call this is the, let's say VC. So first of all, VFS, I need to calculate for V of C, and I need to calculate V of A. So V of C, most likely, this is usually the current that running through multiplied with the resistor. And we already know that the current going through here is 15 amp. So VC is equal to 0.4, which is the resistor, multiplied with 15, which is bad math. 0.4 times 15, 6 volts. So most likely this is VC. We have VC 6 volts. Now we need VA. This is VA. VS is in question. So most likely this voltage, there's a voltage between them. This is positive here. So most likely VA is equal to VC minus 4, which is 6 minus 4, which is 2 volts. Now I have VC and VA, I can get VS. So most likely if I, voltage divider, if you still remember from 211, VA is equal to the resistor here, 0.2, divided by 3 and 2, 0.2 plus 0.3, multiplied with the, so I'm doing a voltage divider. So solving for Vs is equal to reversing the whole thing. This is the value of 2, so most likely okay, 5 volts. So this will conclude the lecture for the first week. Part C is the same thing, but different values. And also the combination from A to B is finding D again for different value. In case you have a problem with these, let me know, I can help you out. Okay, guys, we'll see you in second week lecture. Thank you very much and have a nice day.